Okay, so today we're going to be speaking about calibrating neural networks, and it is interesting to set the context for why calibration is important. So traditionally we have applications where you want a classifier to perform a certain task, and that is the end task. So the end task is the classification. So you might have your black box model, your machine learning model, and that is going to give you a classification output. But the question is, what happens when this classifier is part of a bigger task? So it is only one component in a bigger so it's just one component of a bigger problem. Okay. So for instance, if you have a classifier and that classifier is supposed to give you the probability of different classes, and then those probabilities are used as part of a bigger decision system, then you need those probabilities to be actual probabilities, okay? So, of course, this paper talks about support vector machines, and they go all about support vector machines, but we're going to do it a bit different. We're going to do it with deep networks. So, just as a quick reminder of what a deep network does, if you have an input example X and you have a target, you have an input example X and you have a target for that example Y. What a deep network is doing, and in the most general form, is it's going to try to produce an estimate for that target. So this will live in your feature space, so that is going to be a real number in your number of features. And your Y is going to be, well, it's typically a one-hot target, but let's call it a real number in your number of targets, number of classification classes. Okay? And your estimator is going to do a series of transformations F, where L is the outermost layer, and it's going to do a series of transformations, L minus 1, L minus 2, and so on, until you have your input layer. Okay? So that is what any deep network nowadays is doing. If you make F a convolutional operation, then it's a convolutional network. If you make F a recurrent operation, then it's a recurrent neural network. If you make it fully connected with nonlinearity, then it's a multi-layer perceptron. Okay? And the way you adjust the parameters of this network is through a loss function. Okay? And that loss function is typically defined as a, so if you have your target example and your estimated example, it's going to be the negative likelihood, the negative log likelihood. So you add over all your examples, so let's say you have m examples in your batch, and then you have all your classes, well, I call it T, which is and then you're going to iterate over C, and then you're going to multiply Y times the log of your estimate for Y. Okay? And once you have this loss, you calculate the gradient of each parameter with respect to your loss, and then you update all your parameters following the negative direction of the loss, of the gradient. And that is gradient descent, and that is how we train neural networks. So the question is, once this is trained, so once you have a set of parameters, you're going to be able to produce, let's call this whole function just F. Okay? So you're going to be able to produce estimates for your new examples. So if you have a new example Yn, and you want to transform this into F, so F of Yn given your parameters, or let's call it comma parameters. The question is this the same as the probability of Y given your example, your input example X? Sorry, you have a new X, and is this the same as the probability of Y given X and your parameters? And that is normally not an easy question to answer. So if this F is giving you a one-hot, not a one-hot, but if it's a softmax activation in the output, so let's say that the last layer is of, well, let's call it Z, the logits, let's say that the last layer is a softmax, Z. So you have F, L, small c, where c is your class. So ZC over the sum over all your classes of EZC. So that is the softmax output. If you have 3 classes, this is normalized, so this is going to produce a vector which might look something like 0.1, 0.8, 0.1. Okay? So the question is, does that mean that there is an 80% chance of that class being the correct class and 10% chance of either of these being the right class? And spoiler alert, the answer is no. And the answer is no because this is not actually estimating a probability distribution. This is actually minimizing an error function without taking into account that this actually has to be a probability distribution.
But isn't the log loss there? Exactly, the log loss does enforce probability distribution to be representative, right?
No, that is the problem. So the log loss is going to try to maximize that value. So it is going to try to make your estimate as big as possible.
But log loss gets also punished for wrong confidence. And so that should force it again to a...
Yes, but it is not actually taking any prior on what is the distribution of the data, and it is not updating the... So once you start converging towards the right class, it gets sort of this positive reinforcement, and that activation becomes more and more steep, right? So these sides are not actually calibrated to be a probability distribution. And what we'll see is that that one does not represent a probability distribution either. So the question is, how do we measure that? The answer is, well, let's think how should this behave if it was an actual probability distribution, okay? So if you think that is 80% chance, in principle, if I take all my predictions that said there's an 80% chance of this being the right class, approximately 80% of them should be right. That is the definition of the probability, right? Same, if I take all those that said that is a 10% chance, then approximately 10% should be correct. Note that this does not necessarily relate to accuracy, it relates to how likely is that outcome based on that score that my classifier gave. So a function can be properly calibrated but be a terrible classifier. So the question is, how do we know that, and how do these curves look? So I have a little demo which I'm going to make available. The demo is by no means complete, so if you want to contribute to it, please do. I'm going to put it on GitHub. And so the question is, can we assess if a classifier is properly calibrated? So I took a toy data set, so let's be a bit permissive with the results. It's got 150 training examples, and they can be classified in 3 classes. So this is a subset of the iris data set, which is actually, well, it used to be a benchmark for classification. It's now a solved problem. But this is a subset, which you can find in scikit-learn. So you have some of the characteristics. The idea is you have 3 classes to classify. And